Salam and welcome everybody. Today we're going to start with a family of alkenes and learn more about their reactions. What you remember about alkenes, they have a general formula of CnH2n, and we remember the presence of the double bond in here. From the previous class, we learned that the alkenes are more reactive than alkanes, and the reason behind is the double bond. The double bond can cause a little bit electron density, and as a result of electron density in this area, it makes a lot of reactions. So we're going to cover the three main reactions of this family. The reaction number one will be about electrophilic addition, all right? And we're going to cover the electrophilic addition of hydrogen, of water in form of gas, steam, bromine and chlorine in aqueous. Put in your mind, it must be in aqueous. We're going to cover hydrogen halide like HCl, HBr in the aqueous form, okay? And then we're going to jump to the second type of reactions, which is the oxidation of alkenes. And as well, we have different conditions in this case. We're going to use acidified KMnO4, which works as a strong oxidizing agent. And we're going to use the same material in here. But the difference between the two conditions, we're going to use a concentrated and hot potassium permanganate in here. And we're going to use, in here we have cold and dilute potassium manganate in here, and we're going to get different products as a result of the conditions. So these things will be covered as well. And the last type of reactions is called addition polymerization, which means that you're going to build up a lot of molecules together, okay, starting from a small building block of alkene. The addition of hydrogen gas. Let's take an example of CH2 double bond CH2 plus hydrogen H2, and it must be in form of gas. We're going to apply some conditions in this area. The conditions are, you could use a platinum, okay, or nickel, which works as a catalyst. And you must apply heat. As a result of applying heat in the presence of the two catalysts, the reaction will take place. As we can see, if you look at this carbon in here, you just notice that each carbon makes three bonds, sigma bonds, all right? If you want to add hydrogen, we have two hydrogens, right? Each hydrogen will bond to each carbon in here. So the product will be C, and we have three H's around like this. Here we have hydrogens, hydrogens, hydrogens. We can write that in this form, CH3, CH3. Okay, so this is the addition of hydrogen. Let's take another example. Suppose that I said you have trans butene. Okay, we just made the reaction between this material and H2 gas. How can I deal with such a question? First of all, I have to translate the words and this structure down below. It says that butane, it means that you have 4 carbons. It says that it's 2, which means that the double bond is in the second carbon. We're going to fill the hydrogens here. We have CH3, here we have H, here we have H, here we have H3. How can I translate to be trans? Okay, you have the double bond. Okay, you have C. When we say trans, it means that you have the two opposite substituents. So you could use like this, CH3, and you have CH3 in here, and you have H. Perfect. So this is the trans. This is the trans. Good. I'm going to use, or let's say add, hydrogen gas. You just notice that we will add hydrogen in here and hydrogen in here. So the product will be in here in the presence of nickel or platinum in the presence of heat will be, if you add hydrogen to the first carbon, then it will be CH2, CH3, okay, and we're gonna have CH2, CH3. Then the product in this case is butane, CH3, CH2, CH2, CH3. Another thing to put in your mind, sometimes the addition of hydrogen reaction is called reduction. Okay, and you just remember that from the definition of reduction, gaining hydrogen. Sometimes it's called reduction, and it's used to make margarine. The margarine is a certain type of saturated fats. Okay, that comes from the vegetable oil. Okay, let's go to the second reaction of the electrophilic addition of alkenes, the addition of halogens like X2, which could be Br2 or Cl2. But put in your mind, which is very, very important, it must be in the aqueous form. It must be in the aqueous form. How can I deal with such a question? Put in your mind, we're going to learn the mechanism. If you look for Br2 as a molecule, Br in here, and it's the same thing for Cl in aqueous solution. It's considered as nonpolar in this case, and actually there's no difference in electronegativity. The difference is zero. So how could this nonpolar molecule react with alkenes? We're gonna go and explain all of this stuff. All right. So first of all, you have to put in your mind how the mechanism of this reaction works. So here we have the bromine molecule. As we can see, the bromine molecule contains electrons, right? Like as any element, it has a lot of electrons around. And we notice that there is a double bond that contains as well electrons, right? Perfect. But once this molecule, which means a bromine, approaches to the double bond, then the repulsion will take place. The repulsion between the electrons, between the bromine molecule and the double bond will take place. As a result of that, all of the electrons in the bromine molecule, they will come here. And that's why, because the electrons inside these molecules are concentrated in here, all of them, this atom becomes partially positive, okay? And this one there, partially negative, okay? Once you have partially positive and partially negative, then the double bond can come and attack this bromine because this double bond is negatively charged, or let's say contains electron density. Once it kicks one of these bromine, a heterolytic cleavage will come and the bromine gets out as Br negative. So what will happen as a result of this? As we can see here, we have symmetrical alkenes. So the double bond will be broken, as we can see, and we get one hydrogen here. We have hydrogen. You can take the bromine molecule that is taken in here for any carbon, here or here. We have nothing. Let's say there is no difference because you have identical molecule. So we can add the bromine in here. Okay. It's true that we broke the bonds, but we have another bond that is not formed. Okay, and now what is the next step? This bromine will attack the positively charged carbocation. And then the product in this case is CC, and you have both carbons with two bromine atoms. So this is Br, and here we have HH, and here we have Br. You could write this in terms of structural formula like Br, CH2, CH2, Br. All right, so let's go and jump to the next type of addition. We talk the addition of hydrogen, and this process is called addition of hydrogen or reduction. We just recall that. And it has another name, which is hydrogenation. hydrogenation process, right? And we just added these hydrogen atoms on alkene, right, like this. We add hydrogen in here and hydrogen here. So we had no problem when you have identical atoms in a molecule. The same thing is repeated when we have X2 aqueous, the halogen. We used to put pair 2 aqueous or Cl2 aqueous to the double bond. We break the double bond and then we forming just like 2 carbons with 2 X, as we can see. So in this case, we had no problem when you have 2 identical atoms. We add 1 for this carbon, 1 for this carbon. And the same thing for hydrogen. We add hydrogen here and hydrogen here. But now we're going to go to the next level of this game. We're going to add a molecule that contains different atoms. And now let's see what will be the results. The question number 1, or let's say the first thing that we're going to cover, is the addition of water in form of steam. Okay, water in form of gas to alkene. Okay, to make alcohol. So how can we do that? First of all, we're going to write C double bond, C, like ethene, for example. Here we have ethene. We're going to add the water molecule. Okay, this is in form of gas. And in this case, we have some conditions to make this reaction. So the conditions are, we use a catalyst, which is phosphoric acid, H3PO4, okay, and you must apply pressure and heat. Okay, so once you apply these conditions, then you will get the following issues. You just notice that the water molecule looks like this, OH, right? Okay, you just know that the hydrogen is partially positive, this is partially negative, all right? So according to what you have, the electron-rich area will come and take the partial positive, and these electrons are going to be here. So we'll notice that the formation, the bond will be broken, as we can see, right? You have identical atoms, you have identical compound or symmetrical alkene in this case. All right, symmetrical alkene, which means that like there's no problem if you just combine the hydrogen here or in here. It's the same compound will be produced. So suppose that we're going to make a hydrogen that is bonded to this area, and we still have a positive charge in here, which is the carbocation. The next step is we have OH negative. Okay, this is the OH negative. The OH negative comes again and attack this carbon, and the product in this case will be CC, and we have hydrogens. There's no change in these. We have the same thing, and this is the OH. So as we can see, the product of this addition, the OH and the hydrogen. All right, and you can write this molecule in the form of the structural formula like CH3, CH2, OH. Good. And by the way, most likely in your exams, this form of, let's say, structures is wanted to be written. So once they ask you to draw this structure, you have to use this. Can I write this in terms of skeletal? Yes. 1, 2, and here we have OH. So this is the same as this. All right. The life is not pink, okay, as we thought. What happens if you have unsymmetrical? Okay, unsymmetrical alkene. By the way, there's nothing called unsymmetrical. It's called asymmetrical. But I told you that it was unsymmetrical just to make a distinguish. Asymmetrical means unsymmetry. Unsymmetry means unsymmetrical. Okay, so let's take a propene as an example. CH3, CH, double bond, CH2. All right. If you say like we added water molecule in form of steam and we applied the conditions, which is phosphoric acid and heat, pressure. Okay, now let's say that. First of all, you have to put in your mind that the area that you're going to work in is this area. You're going to add an atom in here and an atom in here. Okay, so the first look that you can see, this compound, it's not identical. Because if you divide this compound to 2 sections, you won't get identical parts. So this is asymmetric compound. So what to do in this case? We have the two probabilities. According to what we know, the first step for adding H2O is catching the H plus first, then followed by the OH negative. All right, so we're going to say like we have two probabilities. Let's start with the first hydrogen. This hydrogen plus could attack in this carbon or in this carbon. So we're going to write all of these possible answers. So let's start with the first one, which is CH3. Let's take it like, let's start the first one here. Once you add one hydrogen to this one, it becomes CH2, all right? And we have this bond, we break the double bond, and then we got CH2. But we just remember something. The double bond in here is broken. And if you just count the number of bonds for this carbon makes 4 bonds, but this makes 3 bonds, and that's why we have a plus sign. Okay, or you can draw it like this. If you just like write the displayed formula first, and then you can translate it to structural formula, it's okay. And we have CH3. Okay, so this is the positive charge. By the way, this is called primary carbocation. This is primary carbocation because if you just look at this carbon in here, it's bonded to one alkyl group only. The other are hydrogen. So once it's bonded to only one alkyl group, we can call it primary. Okay, so this is the first one. Right, perfect. Now let's go to the second property. The second property, when this H is bonded to this one here. So what will be the product? Let's go again. I just need another bright color. Let's use this, right? Okay. We will start from the right. Here we have CH3. It's gained a hydrogen. All right, this is CH3. And we just noticed that we have plus sign because this gained, but this not. Okay, and now we have a carbocation. By the way, if you want to translate it to form of the display formula, which makes easier, just okay, here we have a plus, and here we have CH3. In this case, you just notice that the carbon, which is the carbocation, is bonded to two alkyl. This is 1 and this is 2. All right, so this is secondary. This is secondary carbocation. And now what is the next step? Here we have two carbocations. We have a primary and we have secondary. So what to do to make a reaction? The next step here of the reaction, or let's say the remaining material is the OH. The OH here and the OH here. The OH will attack again here, the secondary, and the OH here will attack this primary, which means we're going to see two products, all right, two products. So we have CH3, C, we have H, and we have OH, all right, CH is in here, okay. And we have another option, which is C, we have H, and here we have OH. We have C, we have H, we have H here, and here we have CH3. Okay, so as we can see, we have two products, okay? We have two products. Once the OH is bonded to the secondary carbocation, and one is when the OH is bonded to primary. So according to what you have, you will get two products, okay? Two products are formed. But put in your mind, we have major and minor. This will be major because it's secondary carbocation, and this is minor because it's primary carbocation. And the reason behind the secondary is more stable. Secondary product is more stable, okay, because it comes from secondary carbocation, okay, and due to something called positive inductive effect, because the alkyl groups, I mean these alkyl groups that are around the carbocation, decreases the charge on carbocation. And that's why you will have two products. One of these is major, one of these is minor. If you have tertiary carbocation, it will be major for sure. And just remember that the tertiary carbocation is more stable than secondary. Secondary is more stable than the primary.